Okay, we have one more section here, section 8.2, to cover before we actually talk about the mathematical relationships of the gas laws. This section is going to cover something called the kinetic-molecular theory, and we're going to learn what an ideal gas is. So the kinetic-molecular theory describes the behavior of matter in terms of particles in motion, right? Kinetic energy is the energy of motion, molecular being the adjective for molecule. So this is the motion of molecules theory, right? How they move around. We're going to make some assumptions about gas particles. These are gas laws that we're going to learn about. So we're going to make some assumptions about gases, about their size, their motion, and their energy, and how they behave. Let's start with our assumptions about particle size. Gases consist of small particles that are separated from one another by empty space, okay? The volume of the particles is very small compared to the volume of the empty space, right? So the actual atoms themselves are very tiny relative to the space they are moving around in. Solids and liquid particles experience intermolecular forces, okay? These forces are forces between molecules. They're close enough together that they attract each other, okay? Remember, solids are locked into position and touching each other. Liquids are touching each other but not locked into a specific orientation, but they are physically intermingling, right? They are right next to each other. And because of that, the atoms themselves actually feel attractive forces to each other, okay? Gases do not. There's so much space between gas particles that they do not experience intermolecular forces, okay? They're just too far apart. So solids and liquids do experience intermolecular forces. Those are attractive forces between atoms. Gases do not. Okay, some assumptions about particles in motion. Gases are in constant and random motion, all right? Constantly moving around. Particles will move until they either collide with the walls of their container or with another particle. And if they collide with the walls of their container, they should bounce off with a similar angle of incidence, okay? Collisions between particles are elastic. You might have heard that term before, probably describing like a rubber band, but at least in the science world, elastic means it's a collision that no energy is lost. Energy is conserved. So, for this reason, the temperature should not change, okay? Particles hitting each other, if it's a fast particle, it hits a slower moving particle, it will make the slower moving particle speed up and the faster one to slow down. And there's masses involved as well, but the idea here is that no energy is lost during these collisions. They are elastic. Okay, so then in terms of particle energy, some assumptions we need to make. There are two factors that determine the kinetic energy of a particle, right? The energy of motion. And those are mass and velocity. In fact, if you're taking physics in the future, this equation, kinetic energy, is equal to 1/2 mv squared, where m is mass and v is velocity. That's the equation to get you kinetic energy. So this is actually going to come up here later on when we learn another one of the gas laws that involves mass and velocity. In a container with one type of gas, the mass of each particle is the same, right? They all have the same molar mass if it's the same gas. But the velocity can be different, right? That means speed and direction, which way it's going. So another thing to keep in mind here with this equation is that larger particles don't have to move as fast to have the same kinetic energy as a smaller particle. Okay, so for instance here, let's say this particle has a mass of, I don't know, 4, whatever unit we want to call it, and a velocity of 1. Okay, right, and then 1/2 times 4 times 1 squared would give you 2, right? Let's say this particle here, which is half the size, has a mass of 2 and a velocity of 2. Well, 1/2 times 2 times 4 is going to give you the same number as the previous one. So these two particles here, if these values were in the same units, would have the same kinetic energy, okay, even though they're moving at different speeds, and that's because they have different masses. This picture here, it's normally actually a GIF, but it's not going to load properly as I'm recording a video. But what would be happening is these particles are moving around the box until they either collide with the wall of the box or with each other, and you can see them actually doing that. And you can see slower ones speed up when they get hit by a faster one, and faster ones slow down when they get hit by a slower moving molecule. If you want to see it in action, though, I'm sure you can Google like gas motion GIF or kinetic-molecular theory GIF, and you'll probably get an image like this. But that's the idea of what's going on here. Some more stuff we need to assume so that we understand the behavior of gases. One of those things is density. Gases are not very dense. They have very low density, right? And that expression is density is mass over volume. Well, gases don't weigh a lot, they have a small mass, and they have a very large volume. They take up large amounts of space. So you would think, just mathematically speaking, small number divided by really big number equals even tinier number. Okay? So to give you an idea here of just how much difference that is, let's take a look at hydrogen gas versus osmium metal. Hydrogen gas has a density of 8.99 times 10 to the negative fifth grams per milliliter. And this is at something called STP, which stands for standard temperature and pressure. Okay, and those values are, the standard temperature is 273 Kelvin, and standard pressure is 1 atmosphere, and we would assume those to be exact values. Okay, but at those conditions, which 0 degrees Celsius and 1 atmosphere, has a density of almost 9 times 10 to the negative fifth grams per milliliter. Osmium metal, which is one of the more dense, I can't remember if it's the most dense metal, has a density of about 22.6. Well, if you take the osmium metal density and divide it by the hydrogen gas density, that difference is about 250,000 times more dense. Okay? And to try to put that into perspective to understand just how much more dense that is, imagine 3 completely packed NFL stadiums, okay, roughly 70,000, 80,000 per stadium. Imagine 3 full stadiums, right, full of people. That would be like osmium metal. Now remove all but one of them, all but one person, and that would be more like hydrogen gas. So hopefully, I don't know, maybe that gives you some sense of just how packed the osmium metal is compared to the hydrogen. Okay, well, since gases have large amounts of space between particles, that empty space can be squeezed into a smaller volume or expanded, right? And then the gas will fill that new space. So gases can compress and expand very easily, okay, if their container allows it to do so. All right, so you can take this container and compress down the gas and reduce the space, or you can expand it and give the gas more space to move around in. Now, of course, if you compress it too much, then you run out of space altogether for these particles to move around in, and you actually start to liquefy it, right? That should make sense there. You force the particles in contact with each other with enough pressure. A couple of definitions for us to also understand about the behavior of gases. Diffusion, you might remember this from biology class. Diffusion between membranes, you're going from areas of high concentration to low concentration. That's also going to be true of gases just floating around. The example that I like to use here, at least at school, is early in the morning. Unless you're like in the cafeteria, you are probably not smelling what's being cooked for lunch. Right? But if you're in the kitchen, you're definitely smelling it. There's a high concentration of those particles. Now, by lunchtime, you can, in most of the building, smell what's being cooked for lunch. That gas, that odor, has diffused through the building. Went from an area of high concentration in the kitchen to the rest of the school, right, a low concentration. Another definition for us to understand is effusion. This is the movement of gas particles through a small opening in a pressurized container. So that would be something like if you poke a hole in a pressurized can, right? You've all maybe done something as well with like, a plastic soda bottle where you slowly open the lid and you can kind of hear it hissing. Similar idea there, right? You've created a small opening for that gas to escape. And that is effusion. So all of these assumptions we're making lead us to what we want to call an ideal gas. And this is if we could create a gas that's going to behave like we want it to, like a perfect gas would, it would follow these conditions. And so you should know these, right, as it says there. Okay, this makes a very good future test or quiz question. Okay, but know the things that make something an ideal gas. And we'll see why this doesn't exactly work here in just a moment, but know these points. The first is that an ideal gas particle, the particle takes up no space. Okay, we know that's not true, but the particle itself takes up no space. They experience no intermolecular attractive forces. There's no attraction between particles, right, like solids and liquids. Gases are in constant and random motion. Collisions between gas particles, it should say, are elastic. And that finally, gases follow the laws under all conditions of temperature and pressure. We're going to see here in just a moment why this isn't always necessarily true, but we're going to assume that it's true. It's good enough for us to use the gas laws that we're going to use here in just a few minutes. But make sure you know these, make sure you get these down, okay? This is what an ideal gas should behave like. Now, after telling you what an ideal gas should behave like, let's talk about why no gas is perfectly ideal. Okay, no gas is perfectly ideal. Gas particles are going to take up some space, albeit very little. Okay, they are tiny, but they do take up space. But we are assuming that they are effectively taking up no space themselves. Okay, gas particles will experience some intermolecular forces as the particles go flying by each other or when they collide with each other as they're bouncing around. Yeah, there's going to be some intermolecular force of attraction between them. Okay, it's going to be a tiny amount relative to solids and liquids, but there is some. Okay, so even though we assume there is zero, there's likely some amount of intermolecular forces. Collisions are not perfectly elastic. Sometimes you lose energy. Okay, and then lastly, under most conditions, though, gases behave close enough to ideal gases that the equations describing their behavior are true. So even though no gas is perfectly ideal for some of the reasons listed right here, it's close enough that we can assume that it's going to be ideal, at least for the equations that we're going to learn starting in the next section. Well, ideal gases and the gas laws work when things are gases. So under what conditions do our understanding of something being a gas start to change, right? What conditions begin to change the behavior of gases? Well, there's two of them. The first one makes a lot of sense, is low temperature, and the second one would be high pressure. Okay, well, what happens if you start to cool down a gas? Eventually, you are restricting the amount of motion, you're lowering the kinetic energy, and you'll get to a point where they're no longer freely moving around, but they will start to stick together and you form a liquid. So as you start to cool a gas, it starts behaving less and less like a gas and more like a liquid. So low temperatures will stop things behaving like gases, and also high pressures. For the same reason I was talking about just a few minutes ago, say with that piston, if you remove all of the space and you just compress the heck out of the gas, eventually you're going to force those gas particles to stay in constant contact with each other, and eventually you can liquefy it. So under these two conditions, what ends up happening is the particles slow down and they get close to one another. This causes interaction between particles, and they become more and more like a liquid and less like a gas. Okay, so that covers us with the kinetic molecular theory and what is an ideal gas.